All right, welcome back, everybody. Don't forget to hit the subscribe button. My subscriber count is still only in the 70s. I said I was going to do a giveaway at 100, but
We need to put posters up. Put posters up in his schools. I guarantee people will see posters.
Put them in every hall.
guaranteed.
Put them in
I'll do
every
it. I'll see what I can do. Okay. Yeah. All right. Section 9.1. Now, excuse me. Chapter 9. We've got now think about this, folks. We got chapter 9. We got a little bit of chapter 11, and then some of chapter 12 to do, right? And that's it out of the entire year. Isn't that weird? Why are we only doing 3 more chapters at the end of the year? Well, because we will take about a week and a half, 2-week break and review for your end of course test that will come up in April. So we really don't have a lot of more material to cover, right? Now, chapter 9 is probably one of the biggest chapters in Algebra 1. Like, my non-teacher friends always ask me, well, what do you guys learn in Algebra 1? What is Algebra 1? And I say, well, we learned how to FOIL, we learned how to factor, and then we learn all about quadratics, which is chapter 9, okay? Chapter 9 is a big chapter in algebra world. Yeah. It's all about quadratics. It's such a big chapter that when you get to Algebra 2, you cover all this stuff again. You go into a lot further depth than we will here in Algebra 1. We just kind of like do an overview and we talk about how to solve these things. But you cover it again in Algebra 2. So this will come back up again a little bit later. Okay, identifying quadratic functions. Identifying quadratic functions, this section is just basically like, okay, what is a quadratic? And what makes a quadratic a quadratic? Okay, so let's start off by talking about our definition of a quadratic. Now you guys have this on your papers, right? The function y equals x squared is shown on the graph that you see. I guess I don't need to hide anything. You see it on your guided notes. You see off to your right. The function y equals x squared is shown on the graph. Notice that the graph is not linear. The function is a quadratic function. Okay. Does anybody remember the unique name of that U shape? Parabola. Good. Parabola. A parabola is any quadratic function. Every single quadratic function must have that shape. Now, that shape can be stretched, compressed, it could be flipped downward, but it must have that U shape look to it. That's what makes a quadratic a quadratic. A quadratic function is any function that can be written in the form ax squared plus bx plus c. Guys, would you whoa, that's not a pen. Would you put something, maybe brackets around that ax squared plus bx plus c? That's kind of an important thing there. That is standard form of a quadratic. Now, we've talked about standard form before, haven't we? Can somebody remind me what standard form is? We talked about it in our chapter 7, our polynomials chapter. How do you put something into standard form? Someone tell me. It's got to go in order, right? In order in terms of what? Good. The values of the exponents. Does that make sense here? Am I doing that same thing here? Yeah. To the second power, to the first power, and then it's not there, right? So it's got to be in standard form. And we're going to write it as ax squared plus bx plus c. Okay. All right. So this is our y equals x squared. Right? Do you notice how it's this parabolic shape to it? Like if I plugged in some values, if I made an xy table, because whenever we don't know what something looks like, it's a good idea to make an xy table. What's happening here? Well, if I plug in -2, what is -2 squared? What is -2 squared? Positive 4. Whenever we square a negative, it becomes positive. Positive 4. What's the square of -1? Positive 1. You square 0, you get 0, and then look, it's going to come back around again, right? We did this in chapter 4, right? We looked at parabolas way back in chapter 4. You should see that symmetry at some point. And that's actually going to be a key term here when we get to section 9.3, I believe. Axis of symmetry. Where is that line of symmetry? -2, 4. Sure, somewhere right there. -1, 1, 0, 0, 1, 1, 2, 4. Notice that I have this, I shouldn't have done yet red. Notice that I have this symmetry line where everything will kind of fold over on itself. Every single parabola will have that as well. Okay, and we'll talk about how we identify what that is and what key part of that is. In lesson 5.1, we identified linear functions based on the change in y as it relates to change in x. Guys, what am I saying right there? Change in y and change in x. What am I referring to? Aligns what? Slope. Change in y and change in x. I'm referring to the lines slope. Guys, is a parabola going to have slope? No, because it's not going to be a constant slope. So what do we look for then? We'll take a look at that. That is what's called the second differences. Guys, this is not written on your papers. I'd like you to do this. Look at the table and its y values. You don't really have to worry too much about the x values, but look at the y values. What's happening in each y value? Well, I go up 1, up 3, up 5, up 7. If it was linear, you would see a constant change in y. It would be like +1, +1, +1, +1 in the y values. Or +3, +3, +3, +3. But guess what happens when you look at quadratics? In quadratics, it's actually a constant second differences. So we had +1 to +3. How much does that change? Up 2. +3 to +5. Up 2. +5 to +7. Up 2. That's called the second difference test, folks. That is called the second difference test. You find differences within differences. Okay, again, this is called the second difference test. Notice that the quadratic function does not have a constant first differences as a constant second differences. Be sure there is a constant change in x values before you try this second difference test. All right, let's take a look here. Let's take a look at our y values. First thing that we should check, is there a constant change in x? Look at our x values. Are they -2, -1, 0, 1, 2? Are they all going up by ones? Yeah, okay, so we're good there. So let's see if this is quadratic. I'm going to do my second difference test. Well, my first differences are, well, how much do I go from -9 to -2? What's my difference? 7, up 7. I'm going to write +7. How much do I change from -2 to -1? Up 1. How much do I change from -1 to 0? Up 1. How much do I change from 0 to 7? Up 7. So if this was linear, I would see it right now. I would see that there would be a constant first differences. So is this linear? No, obviously not. We're in a chapter all about quadratics. So let's find the second differences. What do I do going from 7 to 1? Excuse me? -6. -6. What do I do going from +1 to +1? Ooh. +0. How much do I change from 1 to 7? Is this quadratic? No, this is not quadratic. I must see the exact same number. We'd say that this is not quadratic. You want to see something cool? Now, this is beyond us right now, but take a look here. How much am I going from -6 to 0? How much am I going from 0 to 6? Guess what it would be if you go to the third differences? It would be cubic, raised to the third power. But you'll get that in Algebra 2. A little foreshadowing there. Okay. So that would be not quadratic. That's all we know right now. It's just not quadratic. Try part B on your own. First off, are they evenly spaced x values? Yes. Okay, now do your difference test. Okay, let's take a look. I go, what's 4 to 1? Down 3, right? Minus 3. What's 1 to 0? Minus 1. 0 to 1, plus 1. 1 to 4, plus 3. Okay, so now let's find my second differences. How much do I change going from negative 3 to negative 1? Plus 2. How much do I change going from negative 1 to positive 1? Plus 2. Negative 1 to positive 1, right? Positive 1 to positive 3, plus 2. What do I notice here? Constant. So we can say that this is, yes, indeed, it is quadratic. Okay, so given a table, you can tell whether something is quadratic by the second difference test. Okay, given an equation, I mean, ladies and gentlemen, this can't get easier. How do you know if it's a quadratic or not? Guys, do you see an x squared? So what can we say about this? Not quadratic. Not quadratic. What would we call that? What's my degree of 1 name? Oh, that's terms. No, that's 0. You're close. You're getting closer. Linear, right? Obviously, this is, because isn't that just a straight line? Y equals 7x plus 3, that's just a straight line. So it'd be linear. So we said that that's not quadratic. Is that quadratic? Yeah, right? If I add 10 over to the other side, it'd be 10x squared plus 9. Yeah, it can be written in that ax squared plus bx plus c form. See, I can write it, there's ax squared, bx plus c. Do you notice how I plugged in a 0 for x, for the x term, right? That's going to be pretty important a little bit later on in this chapter. But we can say, because of this x squared right here, we can say that it is quadratic. What if something's got an x to the third in it? Would it be quadratic anymore? No, it would bump up to cubic, right? Yep, okay. We've used this term, right? We've used this term, a parabola. The graph of a quadratic function is a curve called a parabola. To graph a quadratic function, generate enough ordered pairs to see the shape of both sides of the parabola. Guys, this is going to be extremely important. To see the shape, we got to see both sides of the parabola. Okay, we got to see both sides of the parabola. Now, what do we normally pick? What do we normally pick when we're picking points? Noah? Right, we normally pick, with our table, -2, -1, 0, 1, 2. What if we go and we graph and we don't see a full parabola? What should you do? You keep making more points, right? You just go in the direction, obviously, maybe you plotted some points and you only see this. Like, here's my graph, and what if I only saw that? What would you do? You keep plotting points just in the other direction until you see the full parabola. Does that make sense? Okay, so there's going to be some of these that maybe you don't just make 5 points. Maybe you've got to make 7. You know, just you do your -2, -1, 0, 1, and 2, and you're like, wow, I don't see a good look at that graph. I need to do some more points. Okay? So you just got to watch out for that. Okay, what happens if I plug in -2? I want everybody to get out your calculators right now and plug in -2. What do you get when you plug in -2?
4.
Not 2.
6.
6. Thank you. 6. People, use parentheses. Didn't we talk about that at great length in chapter 4? I feel like I should have a button that says use parentheses, so I don't have to say it so many times. Use parentheses when you plug a negative value into a square, or into an x squared. There's 6. Okay, try it again, do -1. What do we get now? 3, that's much better. Guys, you should always, the 0, it should be really easy. You plug 0 in, what's 0 squared? 0 plus 2 is 2. What do I get when I plug in 1? 1 squared is 1, plus 2 is 3. 2 squared is 4, plus 2 is 6. Okay. So when I go to graph this, I hope we see both sides of the parabola. It looks like I do because I see some symmetry in my table. -2 comma 6, -1 comma 3, 0 comma 2, 1 comma 3, 2 comma 6. Do I see both sides of my parabola? Yes. Connect the dots. Okay, what would I take points off here? I would take points off if you didn't connect your dots. I would take points off if you obviously plotted wrong, right? I would take points off if I only see enough points for one side of the parabola, right? You've got to be careful when you graph these things. Okay, let's take a look at this one. Go ahead and make your table. Let's try our standard -2, -1, 0, 1, 2 and see what happens. Guys, am I asking you to graph on this? So should you use graph paper? Yes. Okay, what do I get when I plug in -2? 5? Are we sure? I was going to say, wait a second, -3 times -2 squared plus 1. Guys, look at my calculator right now. Should you include the -3 inside the parentheses? No. What's the only thing plugging in? -2. So the only thing in parentheses should be -2, should be -11. If I plug in -1, -3 times -1 squared plus 1, -2. If I plug in 0, I get 1. I plug in 1, let's see what I get. -3 times 1 squared plus 1, -2. I plug in -2, -3 times -2 squared. Oh, whoa, 1 minute. -3 times just positive 2 squared, sorry. Plus 1. Gets me -11. Okay, so now I go to graph. -2 comma -11. Sure. My graph only goes down to 10, but that's okay. Does your graph go? Okay. -1, -2. 0, comma 1, 1, comma negative 2, 2, comma. Okay, so is it allowed to point downward? Yeah. I still see the rounded U shape. It's just flopped over, right? That's a math term. Flopped over. Yeah. It's just reflected. That's a better word for it. Reflected. Okay, questions about that? Okay. Now, as shown in the graphs in example 2, some parabolas open upward and some open downward, right? So what are the rules? How do you know when something opens upward, or how do you know when something opens downward? Go ahead and underline these rules, please, or just make it a bracket around them or something. Okay. I want to make note of something here. Parabola opens upward when a is greater than 0. What's another way to say a is greater than 0? What's another way to say that? What am I implying there when I say a is greater than 0? It's positive, right? When a is, write that in there, you should write in red pen. When a is positive. Okay, so what am I implying when a is less than 0 then? Negative. Okay, write that in there for yourself. Because when a is greater than 0, that's a little weird. You can just say when a is positive. Okay? You know what I always say? When a is positive, it's happy. It's a smiley face. Okay? It's a smiley face. When a is negative, it's a frowny face. I'll be here all week, folks. I'll be here all week. I'll be here all week.
I thought it was gonna rhyme.
Okay, so let's take a look here. Now, what is my a value here? 5? -3. Guys, is this in standard form? Let's put it into standard form. Y equals -3x plus 5x. You see that? It has to be in standard form. So in this case, because it's ax squared plus bx plus c, what would my a value be? My a value is -3. Now, the only thing we know now is that if it's positive, it opens up. If it's negative, it opens down. So is this opening up or down? This is opening down. We're going to learn a lot about graphing, especially in section 9.3. We're going to spend a couple days on section 9.3 because it's all to do about graphing. Hey guys, everybody eyes up here real quick before we move on. What is my c value in this case? 0, not 0x. An x should never be in an a, b, or c value. A is -3, b is 5, c is 0 because it's not there. Okay, good. Let's try another one of those. Ooh, yikes. Okay, is this solved for y? No, because it's not in standard form, right? So, what do I need to do to put this into standard form? Add 1/3 x squared over to the other side. Now, does that combine with anything on the right side? Does that combine with my x? No. So I've got 1/3 x squared plus x minus 3. Again, my a value is next to my x squared. My b value is next to my x. My c value is at the end. So what is my a value in this case? 1/3. Do I care that it's a fraction? No. What's the only thing that I care about here? Negative or positive. It opens up. This opens up. A value is 1/3, so that opens up. It's happy.
I see this smiley face. Maybe that was unintentional.
Oh, yeah.
The arrows are smiley face.
I didn't even mean to do that. Now, what's my b value in this case then? It's not x, just 1. What's my c value? -3. Good. It's a good idea to start picking those out. Okay, last one here. Okay, does this open upward or downward? Downward. Good. Questions there? Feel okay? Good. All right, another key point that we're going to learn about any parabola is called its vertex. Yeah, don't turn your paper over yet. I need you to be looking at this box down at the bottom of the paper. The vertex. That's a very, 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 very important piece of information that every parabola must have. Now, it could be either a bottoming out point or a topping out point, right? It could either be a top point or a bottom point. We call that top or bottom point the vertex. Now, another name for it is called the maximum or minimum value. Obviously, if it's bottoming out, that's going to be a minimum value. If it's going this way, if it's topping out, if there's a top to it, that's going to be a maximum value. It's going to reach a highest point. Okay? Come on, get away. Now, how does that tie into what we just learned? Well, if A is positive, that means it's a happy face. It will have a minimum value, not a maximum, right? Because it's going to have that bottoming out point. If A is negative, then it's a frowny face. Then it's going to be a top point, or in other words, a maximum value. Okay? Now, take a look at where these are. For right now, we're just going to be pulling them off the graph. Okay? As soon as we get to section 9.3, what we're going to be doing is actually calculating them out. Like, what if I don't give you the graph and you have to figure it out by hand? Well, there's an equation that you have to use to figure out what a maximum or minimum point would be. Okay? So let's take a look. Flip over your page now. Identify the vertex of each parabola, then give the minimum or maximum value of the function. Okay, so what is the vertex of this parabola? -3, +2, right? -3, 2. It's right here. -3, 2. Now, is that a maximum point or a minimum point? It's a minimum because it's got a bottoming out, right? There is a lowest point. Minimum. And we can say minimum at. Now, here's the tricky thing. The actual minimum value of the function is the y value. Okay? Now, if you gave me x and y value, I probably wouldn't be mad at you. But the true minimum value is the y value. Okay? That's the true minimum value. So the vertex is at -3, 2. The minimum is at 2. The state test loves to just give you the y value just to make sure that you know. They would say, okay, the minimum's at 2. Where's the x value that that happens at? It's actually just asking you for the vertex. Okay. What about here? Where is the vertex of this parabola? 2, 5, right? The vertex is at 2, 5. Now, is this going to be a minimum or a maximum value? It's going to be a maximum value. Max at 5. And you just take the y value straight off of the vertex. Make sense? Now, unless a specific domain is given, you may assume that the domain of any quadratic function is all real numbers. That's a very important statement that I just made. You can assume that the domain of a quadratic function is all real numbers. Go ahead and underline that or box that or do whatever you need to do. The domain of any quadratic function is all real numbers. So what about the range? Well, the range is dependent upon whether it opens upward or downward. Okay, the range depends upon whether it opens upward or downward. So I ask you for the first example that we have here, the one that there's space for, is what's the domain of this function? I just told you what the domain of any quadratic is. What's the domain of this one? No, what's the domain? Looking at all the possible x values. I had to just underline it and bracket it. What's the domain of any quadratic? There you go, all real numbers. The domain is all real numbers. Oh, that's talking about the range. Okay, the domain is all real numbers. I'll just write it up here. Okay, so what's the range? What's the range? Now, think about y values, right? Guys, do I have a possible y value at 0? What about -1? Is there anything down there at -1? What about -2? No. What about +1? Yeah. What about +2? Yeah. +3? Yes. So where do I start? I start at my minimum point. Okay. And I want all values above that, right? I want it like the arrow is going to look like that, right? I want all values above this line. So the range is actually going to be y is greater than, whoa, that's not a pen. Greater than or equal to 1. Y is greater than or equal to 1. Okay, that's the range. This is how we would write it. The range, y is greater than or equal to 1. So there's the domain, there's the range. Greater than or equal to 1. So let's do some domains and ranges. Let's do some domains and ranges. Hey guys, what can you write about the domain of all three of these problems? All real numbers. The domain is always going to be all real numbers. Because think about the x values that I could plug in. It's going to go forever left and right. Right? There's no limitations on the x values that I can plug in. Okay, but what about the range? What about these y values? Where do my y values start? At -3, right? I come down at 0, there's nothing. At -1, there's nothing. At -2, there's nothing. At -3, it starts. Now, do I want all numbers above or below -3? Below -3. Less than or equal to -3. Okay? Do I care that this happens at -1, 2, 3, 4, 5? This is at -5, -3? No, I don't care about the -5 piece of it. That's a good portion, that's a good thing to know because it's part of my vertex. But do I care about it for my range? No. Why is this now less than or equal to instead of greater than or equal to? Because it's pointing downward instead of pointing upward. Okay, it all depends on whether A is positive or negative. What's the domain here? All real numbers. Okay, what's the range of this? Yeah. Okay, I like, whoa. Are you on this one?
Yeah, y is greater than or equal to 1.
Good. And he kind of let the cat out of the bag there a little bit on the last one. The domain, everybody understand for part B here? Okay, on the last one, the domain again is all real numbers, but the range is all y's less than or equal to 3. Less than or equal to because it's a maximum point. Okay. Homework is up here, page 595, numbers 22 to 38. Make sure that you're using graph paper when I ask you to graph. Deal? All right, say bye to YouTube, everybody.
Bye, YouTube. Bye.
So long, farewell.